Hello everyone, my name is Ashley Goodnight and this is my Lab 5 presentation. First, let's move to the introduction. The purpose of this lab is to predict the motion after a collision between two objects of equal mass and compare the results to the actual observed motion data. We care about the conclusions and the results of this lab in order to apply our knowledge of two main physics concepts: conservation of momentum and conservation of energy, as well as gain experience taking real observed motion data, inputting it into Tracker, and coding in GlowScript. Now onto the summarized results. Here is a more in-depth summary of my results. In GlowScript, I successfully created a model of the elastic collision of carts using Tracker and GlowScript. There were slight discrepancies between the observed and predicted motion due to a variety of error sources, discussed later in the presentation. For now, let's move on to the Tracker program. Here we can see the Tracker program with the inserted clip. As always, I trimmed the video to capture the point his hand was off of the cart after the push all the way right before he stopped the carts. For all of these frames, I hand marked the position in the lower right corner of the carts. In order to calibrate these position points, let's look at the main assumptions. I looked up the spec sheet of the equipment used in the video. I found the company Pasco and their ME9454 collision cart model. The only dimension provided was the mass of 0.5 kilograms. Fortunately, I found a demo on their website that I plugged into the Tracker with a known length of the track, ending up with the length of the cart as 0.162 meters. I calibrated the Tracker video you saw on the last slide with this distance. There's still a couple more values we need for our code. One of those values is the initial velocity. I used the equation in the lower left corner. Velocity equals the displacement over change in time. I calculated velocities of 0.38 meters per second and negative 0.43 meters per second, respectively. Now let's look into why I needed the initial velocity. In collisions, there's always conservation of momentum, which uses those initial velocity values we calculated. However, you'll notice that still leaves two unknown variables, both final velocities. Lucky for us, this was an elastic collision, meaning we can use conservation of energy as a secondary equation. We are also solving for a special case. We have two objects colliding that have the same mass. That means that we can remove the mass quantity from our conservation of momentum equation. We can also remove the half times mass quantity for our conservation of kinetic energy equation. So, when we solve for the final velocities, we find that the final velocity of the first object equals the initial velocity of the second object, while the final velocity of the second object equals the initial velocity of the first object. Now let's implement this into the code. First, I wrote the code for the visualization of the objects, their trails, and the origin. Then I created position curves for each of the objects. I inputted the initial values like their mass and velocity vectors. The last things I added before the calculation loop was the time settings. Inside the calculation loop, I added the speed of the program, the simplification for conservation of momentum and energy, updated the position of the objects and time, before finally plotting their movement. Let's look at what the code produced. Here is my GlowScript results. As you can see, the collision motion looks like the Tracker clip, but let's plot the Tracker data on the same graph for better comparison. Here is the observed versus predicted plot. As you can see, they are the same motion, but slightly off. This is likely due to multiple reasons. One source of error could be due to my, unconventional calibration methods in finding the length of the carts. The second source is human error. It's impossible to select the exact point mass for each of the frames in Tracker. Next, we made the assumption that there are no net forces acting on the carts, but there is friction from the track acting on the wheels that we ignored. Lastly, purely elastic collisions are impossible in real life. There will always be some system loss of the energy due to thermal, chemical, and sound transfers or changes. Let's discuss this concept more in depth. Understandably, you might be asking yourself, wait, you said earlier this is an elastic collision. And in this class, we would categorize this as an elastic collision. In the tracker video, we see two objects collide and bounce away from each other like an elastic collision. In the case of inelastic collisions, two masses stick together and move as a single unit, which definitely does not describe this tracker video. With that, I conclude my presentation. Thank you for watching.